Welcome to Energy Radio, a podcast by CEM Engineering. Welcome to episode 18 of Energy Radio. On this episode, we talk with Scott and James of Zinc about energy storage. Guys, welcome. This is great.
Thank you so much for having us. Yeah.
And this is fun to see Scott again.
Yeah.
New baby daddy.
4 days. 4 days old. Yeah.
Yes, good. And James, good to meet you for the first time.
Very good. Yeah.
Why don't you guys just give a bit of a brief intro on kind of what brought you to Zinc, and then we'll dive into the company and who knows where we'll go. So James, maybe I'll start with you. Just a quick summary of how you got to this point.
Sure. Yeah. So I've always wanted to lead a clean tech company. I've always been very passionate about the environment, and my background is in mechanical engineering.
Right on.
I started working in that industry in hydrogen fuel cells initially, and then in microhydro and geothermal. But my skills and affinities have always lied with the business side of things.
Okay.
So after my MBA, I started working at Bain & Company in the strategy consulting area. And then when I left that firm, I started looking for this type of opportunity. And I actually took 8 months without a salary just looking for this type of company.
Okay.
And two things became very obvious. One is that it was going to require a lot more patience than just 8 months to find the proverbial diamond in the rough.
Wow.
And number two is that I was rapidly losing cash. My savings was going like this when I wasn't working. So I joined Mars, which is a startup incubator in Toronto, and figured that would be a great place to put myself to have purview to the startup landscape. And after 2 years, very happy to say that I met the founder, was introduced to him, and it was just very obvious. The value proposition of this particular technology and the rising tide of this industry was very, very compelling. And so I really felt like I had found it, and I joined the summer of 2018. So I've been the CEO for about 18 months.
Awesome.
And the company's been around for about 7 years. But we'll get into that history.
Yeah,
So it was an interesting transition for the founder to be aware that he really needed someone new to take the helm for the next chapter of the company.
Yeah, that's a whole discussion in and of itself. That whole organizational theology about founder and next gen, and for sure. So you have this sense that you want to be in clean tech, you want to be a leader in clean tech. Mm-hmm. And you're so kind of committed to that you burn through cash, you don't work, you're patient, and clearly, finally, it's paid off.
Yeah,
cool.
It really has. Yeah.
Good. And Scott, I mean, I know your story when you were with the Green Engine guys, but would love to hear it again.
Yeah, absolutely. So prior to Zinc, I was with GE Power, mainly focused on the Yumbacher business, CHP, working quite a bit with CEM.
Yes.
I'd say near the end of my time there, we started to see more and more projects go to batteries and energy storage. So that was one bit of an awakening. But also, I mean, we're in an industry that's in transition, right? There's a lot changing, which is exciting. That means lots of opportunity. But I met James in December of 2018.
Yes.
2018, and I actually, the first time I met him, he showed up, suit jacket, backpack, and a helmet. And I'm like, I like this guy.
Yeah,
right?
I know you a little bit. I can see how you like that. Yeah.
And it was probably a stretch of about 6 months while we were talking. And the first, I'd say, formal meeting I had with James and then our founder, my impression was that, hey, you have a neat technology, and I could see the market fit at the grid scale. Balancing renewables, but I didn't quite see the entry market for it yet. And I didn't see even the way to get to market at small size projects. And that was my first reaction. But then over a period of, say, 3 or 4 months, it was incredible the amount of cool applications we were coming across. So that was really part of my due diligence process, and found that, hey, this is a neat tech. I could see the path to market. Mm-hmm. And James and team had recently secured money. They're ready to bring someone on. And I joined in July of this past year.
Okay, so we're getting close to the 1 year mark for you.
A
couple months away.
You got it.
Good,
absolutely.
Good. Excellent. Yeah. The fact that you gravitated towards James in a bike helmet and a suit reminds me of, we met up in Calgary once for something, and you told me that the weekend you came in early to go backpacking in the mountains, and you and your wife, and you woke up and there was like a foot of snow on your
That's
tent
right.
or something. And it was like, it was either spring or fall. I can't remember when it was, but I just thought to myself, that's not on my list of things.
September, and meant to be summer camping is a full-on snowstorm.
You're right.
But
but you were unfazed by it, so
that's his nature.
Yeah. Good. So tell us about Zinc. Where does the name come from? What's the company about? Just give us your elevator pitch on Zinc, and then we'll dive deeper.
Sure. So Zinc is a company focused on long duration energy storage.
Okay.
And the whole thesis is that with the rapid expansion of renewable energy, we know it's intermittent. And the most common thing for people to talk about are the short duration intermittencies. It's the California duck curve, or it's peak shaving.
Yes.
But if you extrapolate out the growth of renewables to the point where they are our core energy supply, it's not about the daily cycling issues. It's about multiple days. It's about multiple days where there's no sun, right? Or in California's case, an entire winter season without wind or sun, right? And so you start needing to talk about days, weeks, months of storage.
Okay.
And so that's really what our technology is focused on.
So just so I'm clear, when you say long duration, you're talking your increment is probably starting at days. Is that
our minimum duration is 24 hours. We look at 24 hours and longer.
Okay.
Batteries like lithium lead acid, you're talking about applications of 1 to maybe 3 hours.
Yes.
Flow batteries, you're talking maybe 4-8 hours.
Okay.
We're talking truly long duration.
Long duration. Okay. Wow. And at the guts of the technology, I mean, your name kind of gives it away, but it's some kind of zinc compound, or like maybe compare and contrast, because everybody's all hot and bothered about, lithium right now. It's the, Tesla and Elon Musk and everybody's making lithium famous, but contrast it with that in terms of the guts of the technology.
Yeah, so maybe I'll just quickly explain how the technology works.
Yeah.
So it's a zinc-based technology, and it's a cell-based technology. Okay. So one of our cells is a little bit bigger than the size of a desktop computer, if you picture a box about that size. And the whole thing is filled with a bath of electrolyte and dissolved zinc in it.
Okay.
And we have a series of charging electrodes at the top and discharging electrodes at the bottom. So when we inject in energy into the system, the zinc precipitates out as physical metal on the electrodes at the top.
Yes.
And we have a wiping mechanism that wipes it off like a windshield wiper, and it falls via gravity and collects in the bottom of the cell.
Okay.
So that physically free zinc metal is stored energy.
Okay.
It's a wild concept.
Yeah.
We're literally what we call metallizing energy. We're turning energy into electrochemical potential energy. And so that zinc sitting there is the energy. And when we need it, we inject in air into the system, and the oxygen in the air dissolves the zinc back into the electrolyte. And the dissolution of the zinc is what releases the energy.
Okay.
And now that the zinc is redissolved back into the electrolyte, the whole process can be repeated, hence the rechargeability of it.
Right, okay.
The reason this is so important is that batteries, power and energy are intrinsically coupled. Like there's a fixed ratio between power and energy.
Yes.
So if you want more energy, you have to just buy another battery, which comes with more power. And you may not necessarily need both of those things. Our technology, we've decoupled power from energy, because by storing energy in physically free zinc metal, if we need more energy, we just make a bigger cell, so a bigger box, effectively, with more electrolyte and more zinc, and that's the cheapest parts of our system. And so we can create longer and longer durations of systems depending on market application, and in a very affordable way.
So to decouple energy and power, basically you make the bath bigger, but the power rating stays the same. Is that right?
Correct.
Am I understanding?
Correct.
Whereas in a conventional battery, if you need more energy, just inherent in the nature of the battery, you need to buy, just by buying more, you get more power as well, typically.
Just to put this into with numbers, so like a lot of people are familiar with the Tesla Powerwall.
Right.
The Tesla Powerwall is 5 kilowatts, 13.5 kilowatt hours, meaning it's got about 2.5 hours of runtime.
Yes.
The average Ontario household uses about 40 kilowatt hours a day. So if you needed enough energy to sustain you for the entire day, you'd need 3 Tesla Powerwalls.
Yes.
But interestingly, you now have 15 kilowatts of power.
Right.
The average home doesn't need 15 kilowatts of power.
No.
So with our technology, we can right-size systems so you still have 5 kilowatts, but you have the 40 kilowatt hours
I
if you
see.
need, and so on and so forth. So we can tailor it to customer applications.
And because you mentioned it's the kind of the lowest cost piece of your system, do I understand that in terms of incremental dollars per megawatt hour, you can be pretty competitive because it doesn't cost a lot to add energy.
Exactly.
Right? Okay.
So the cost follows an asymptotic curve, right?
Sure.
With batteries, you're always going to pay that same cost
Yeah.
for a system. You're just buying more and more and more of them. With
Yes.
our system, the cost comes down the longer the duration you need.
Right.
It actually reinforces our own value proposition.
Yeah. So this technology, is this like, has it been around for a while? I mean, it's not something I've heard a lot about, but like, how long has it been around? Does the founder, is he just this, brilliant scientist that discovered it? Like, has it been around for a while?
So I think it's maybe important to share the history.
Yeah, please.
I'm hogging the mic here.
I'll
do this question.
Please do. You're good. You're great.
So our founder, Dr. Gregory Zong, he is a PhD from MIT in Columbia.
Wow.
Very brilliant guy. And his whole background is in electrochemistry.
Okay.
And he was hired by Teck Resources because Teck Resources, as one of Canada's largest mining companies,
Yes.
owns the world's largest zinc mine, the Red Dog mine in Alaska.
Okay.
They had a thesis that if they could make an investment into an energy storage technology that was based on zinc, they could create demand for their metal.
Aha.
And zinc has been known since the 60s to be an incredible electrochemical material. People just haven't quite figured out how to harness it properly yet. Anyway, so he joined Teck, and for 20 years he spent his career researching this particular subject matter. In fact, he wrote the world's only book on zinc electrochemistry.
No kidding.
He literally wrote the book on the subject.
Wow.
And so anyways, for 20 years, he looked at different technologies. He studied it in depth. And Teck actually ended up making an investment into a particular company.
Okay.
And he led that process. But what he realized is that every zinc-based technology out there was just another form of battery. It was a short duration technology. It was a zinc air battery or maybe a zinc bromine flow battery. It's intended for a few hours. But what Greg realized is that zinc has an incredible set of electrochemical properties to be an energy carrier. So if he could figure out a way to store energy in physically free zinc metal,
yes,
he could enable long duration storage. And that was his impetus to leave Teck and start this company.
Okay. So it really, to bring it back to first principles of science, the potential energy is stored in that freed zinc is essentially how it works. Yeah.
Correct.
And does it, Scott, does it have different, energy storage is kind of the broad term. It can have multiple different applications, and you guys are talking about long duration. We are starting to talk about energy storage as a grid stabilization. Like, does this technology fit that application as well, or is it primarily long duration?
Yeah, so it can. The way we're framing our go-to-market is in 3 horizons.
Okay.
Starting with remote, resiliency, and then grid-scale renewables.
Okay.
And,
really? Okay.
And we say it that way for us, our first projects will be in the kilowatts to the hundreds of kilowatts scale.
Oh, really?
Right.
Okay.
Smaller scale, and that's just really where we're at
Yes.
right now. We're early commercial. We're in the process of going to market. So our first applications in remote, it's really about displacing diesel in off-grid sites, off-grid communities, and the real benefit of that application is we're displacing diesel. The value proposition is very strong. Mm-hmm. And so the idea is to combine solar or wind with storage, but to be able to, in typical off-grid scenarios, if you had a microgrid setup with solar and storage, you still need a diesel backup because the batteries might only last a couple hours, right? And
right, yes.
if you have a day with no sun, right, you're stuck relying on diesel.
Yes.
And so what we're designing are solutions that can go 100% renewable, right?
Wow.
Energy storage system that can sustain the site even if there's no solar or wind energy for a day or two.
Right, okay.
And so that's really the first application that we're going after. And followed by, and somewhat in parallel, is our resiliency application. And we think of that as backup power, but with additional benefits. And I say that because, as you know, with backup power, you're really paying for an asset that, for the most part, sits there.
Yeah,
right?
You hope you never use it.
You hope you never use it.
Yeah.
And so we're looking for applications where there's additional benefits to that backup power. And a great example right now is in California.
Yes.
Right, where, of course, with the wildfires, they're really looking for microgrid solutions that can provide at least 2 days of backup in the case of an outage or a fire prevention shut-off.
Right, yes.
But the nice thing about California as well is they have a very wide time of use energy spread, and they even have special rate structures to help incentivize storage. So you could charge at maybe 5 to 10 cents and discharge at close to 40 cents during peak time.
Wow.
So the application in California would be, hey, this system can cycle daily for 9 to 10 hours and still have enough capacity to sustain the customer during a grid outage.
Oh, I see. So it could play in both the energy arbitrage market and in the backup energy. I don't want to call it generation, because it's not really generation, but backup energy market. Okay, interesting. And then the third one you said is...
Third, renewables, and that's really a longer-term target. We know that, like, the grid of the future will need long-duration storage to really get to the high renewable penetration targets that many states, provinces, and countries are targeting. But those are really projects in the megawatt, even gigawatt scale. It's maybe 10 years out for our tech, but what we're thinking at that point right now, the form factor of our technology is cell-based, and longer term, we see it as more of a custom-built or purpose-built facilities using our same technology, and it still has the inherent low cost of zinc and electrolytes to add energy capacity. So it's the same technology, but we expect it to look different at that time, and we've been thinking through that.
Are you thinking like, buildings and like that size scale? Like you have, you walk in and there's baths of zinc. Is that kind of what you're thinking? And
it could be. And it could even be. What's really neat about our technology is that there's a separate charging and discharge assembly.
Yes.
And so we could even separate those in the building.
Yes.
Right. You could even picture forming a lot of zinc in the summer months and having that stored and using that in the winter. And so there's a lot of different directions our technology could go with this, using the same electrochemistry principles and our same patent portfolio.
I just had an interesting thought. So does it to discharge the energy, the potential energy, does it have to be zinc that was formed through the process? Or like you think of a diesel generator and you can deliver diesel in a long outage to site. Can you do that with zinc? Like, can you deliver, if you have a long outage and you have can you deliver zinc, incremental zinc into the system, or it doesn't work that way?
So today's version and embodiment of the technology, you can't do that.
Okay.
However, that is a possibility.
Really? Wow.
And we've when we do our big blue sky thinking about where we dream this technology could go, I have a lot of experience working in Chile, and I know that I'm familiar with a lot of the dynamics in the Atacama Desert as an example, right? Like, it's the highest solar radiance in the world. The cost of solar is effectively zero, right?
Yes.
It's a variable cost. And so you could produce just tons and tons of zinc and literally ship it. And there's infrastructure for that, right? Like, so you have the discharging aspect of the cell in certain markets, like in Southeast Asia, Africa, or whatever. And you have the charging located in these geographic areas where there's a lot of cheap renewables, and then you ship it. It's no different than drilling for oil in a particular place, putting into a tank, and shipping it somewhere to be used, right?
Yes,
so yes is the answer to your question. Yeah. We don't have the embodiment of it yet, but
theoretically and practically it could be done at some point. Yeah. So where does the supply chain for zinc? What is it? I mean, I think you mentioned the tech. The impetus for a lot of this came because they wanted to generate a market. But the flip side is if this takes off, I mean, you've hired a great BD guy, like this is just going to take off, right? So is the supply chain piece a concern for you? Like, are there limits to it at some point?
You can never be absolute about your answer with this sort of stuff.
Yes.
But we don't think so.
Okay.
And the reason is, first of all, there's about 480 megatons of zinc in the world's global reserve.
Sounds like a lot.
It's a lot.
Yeah. Okay.
We've done some back of the envelope math. If we were to use our technology to balance 10% of the world's renewables by 2030, we'd use about 11 megatons.
Oh, okay.
So really, we're not going to move the needle on that.
Yes.
And the second thing to buttress that is that 40% of the world's annual consumption of zinc actually comes from recycling markets. It doesn't come from harvesting new zinc.
Oh, really?
And so, and so it actually is a relatively sustainable material in that regard. So you're not really going to be tapping into that 480 megatons anyways. And the last couple points I'll make is that zinc is a global resource, and as you know, it's abundant. And I find it very interesting that the world is pushing the direction of lithium ion. And China controls 65% of the world supply. Chile and Australia have another 15%, and then 20% is sort of scattered around.
Sure.
Have we not learned the lessons of OPEC when a particular group of nations control a very valuable resource in the world and have pricing control over things like that? Like we're literally going down the direction of handing the keys over to China, Chile, and Australia, mainly China, and versus something like zinc where there is no global superpower of zinc. It's diverse across the world.
Now, so that's very intriguing, and I guess it brings me to the question about one of the knocks on the lithium-ion space is this, particularly because 65% of it comes out of China, where a large majority of their power is generated from coal, particularly at the mine mouth. You bring this lithium-ion technology to a green market like Ontario, and you say you're greening things because it's being charged with renewable. But if you draw the envelope big enough, regardless of what you do in the disposal, on a creation side, you have a lot of carbon emissions. Is that same? How do you guys get asked that question? Is that applicable to you, or because it's distributed? And you're pulling it out of the ground differently, or this is a new element for me.
Yeah, so we've looked at the life cycle of greenhouse gas emissions on our tech in a few different applications. And I mean, one thing with any energy storage, you want to be charging it ideally from renewable energy.
Yes.
Right. The cycling, the daily cycling, is where the vast majority of the carbon intensity will come from.
Yes. Okay.
And I think you need to look at it in terms of what you're displacing. So when displacing diesel power, any upstream emissions really get almost washed away.
I see. Okay.
Right. So that's been our experience, and we've looked at it as well in terms of where the zinc is being mined, where raw materials are coming from, being trucked to, say, a central location for processing. And even end-of-life disposal. So we've looked at it from the whole aspect.
Yes.
I'd say still it's being, all of those things get washed away when you look at what you're displacing.
So you're not disputing the front end and disposal piece. All you're saying is that if you do want to draw the box that big, the middle portion of the life cycle, you're so far ahead from a GHG avoidance perspective that the ends are somewhat kind of, they get, it's not great, but the net is positive. Is that what you're saying, Scott?
I'd say that.
Yeah,
And also in comparison to lithium, we're a step ahead, a couple steps ahead anyway, just because of the factors that James mentioned, that zinc is mined more than just a few locations. So the distance to transport it is easier. It's often from recycling markets, it's often a byproduct of other mining. It's often found in gold mining, right?
Okay.
So it's just there.
Yes.
And so with those factors, we're in much better shape. And then end-of-life recyclability and reusability of our product, that's another aspect where there are there are pretty significant recycling challenges on the lithium ion side right now. Whereas with our technology, I mean, one, the electrolyte and zinc can be reused in further products, which is quite neat. And but if not, it can all be recycled as well. So
cool. That's good.
It's a good story in terms of recyclability and reusability at end of life.
Okay, let's pivot back to the business to Zinc. There was some recent news. I think you guys got a big grant or something. Is that right? Can you tell us about that?
Yeah. So there's 4 big things.
Oh wow. Okay.
In November, we closed a $3.5 million equity raise.
Oh, cool.
Which was it was a long slog, but
yeah,
we did
I bet.
it. The day after
Had you done that before, James, in your career?
I hadn't raised money before. No. So I knew that I had to do this as part of what I was signing on to do.
Yes.
And I was excited to do it. And I figured, I felt confident with it.
Yeah.
Just because of the strength of the value proposition.
Yes.
It took longer than expected, but everything does.
And at the risk of probing, is it like angel investors or like where does the equity come from?
It's actually a mix. Okay. So we have our lead investor is based in Chicago. Okay. Energy Foundry is their name. Interestingly, they have not made an energy storage investment to date. We are their first.
Yeah.
They only do 4 deals a year.
Wow.
So and they look at about 800 to 900 every year. So the fact that that they've invested in us, I think, is an amazing vote of confidence. And then we have a number of other local funds here: Emerald Capital, the Investment Accelerator Fund, Sustainable Chemistry Alliance. We really have a good consortium.
Cool.
And then we also, fortunately, have some really significant angel investors.
Awesome.
I won't mention their names,
sure.
but they're fantastic individuals who really care about the business.
Yeah.
And I have to say, the entire syndicate, everyone is really involved. When I have a strategic question or whatnot, or we're looking for help in a particular area, I'll blast out to the investors, and you'll almost always get 5 or 6 replies being like, "Hey, I think I can make this introduction."
That's huge.
How about this? Yeah. So very good.
Cool. So that's number 1.
That was number 1. Yeah. The day after that, we found out we won a grant from Sustainable Development Technology Canada.
Okay.
The reason this is important is that they were the group that awarded and partially funded our demonstration system.
Okay.
So we have a demonstration system up and running in Etobicoke.
Oh.
It's been running for about 18 months.
Okay.
And they were so pleased with the success of that project that they wanted to be part of our early commercialization.
Okay.
So we got $2 million there.
Wow.
A month after that, we found out we won another grant of $700,000. This one's still confidential, so we can't talk about it. And then in January, we found out we won, or one of 10 winners of Breakthrough Energy Solutions Canada. This was a competition put on by NRCan, Natural Resources Canada, Breakthrough Energy Ventures, which is Bill Gates' venture capital fund,
right,
and BDC, a Canadian fund.
Yeah.
And so the money comes in the form of a grant, and there was $20 million allocated to these 10 winners. But interestingly, Breakthrough Energy Ventures and BDC have also each allocated $10 million as matching potential equity investments. So they're not beholden to make the investments, but so not only do we have the grant, but we also now are in line for them to work with us to see if we can potentially get some equity. Okay. So in grand total, it's about $7.8 million, 3.5 of it equity, and 4.3 non-dilutive grants.
Wow.
So
that's cool.
Pretty big 2 months.
Yeah. Wow. So Scott can come back in on Monday. Like you got enough money to keep paying him and his new baby.
This guy is fantastic. He put together the applications for the latter 2.
Cool.
We're very, very thankful to have him on the team.
Yeah, agreed. He was a loss to Ineo, but that's in the background for sure. So what did the next kind of 6, 12, 24 months look like? You're on the road to commercialization. You're there. Can I go to your website and buy one? Like, where are you going next with this?
We are our next step, and this is really what the grant money is for. And I think we're quite lucky to live in a country like Canada that supports technologies like ours. And we're at a stage that it is challenging for young companies, right? Going from like an in-house demonstration to in the field.
Yeah.
Right. And that's really what this money is there to support. So our next couple years, I'd say, I'll lay it out. There's maybe three main tasks, and the first, we're working on productizing our technology, and that starts with the pilot we have in house right now. Is really hand built by our technologists.
Okay.
Each cell. So we're in the process of properly manufacturing those cells. So we have a team working on SolidWorks, designing every component such that they can be manufactured externally in pieces. We'll assemble in house right now. So that's the first bucket.
Okay.
Properly manufactured cells. The next is we have our first demonstration project lined up. It's actually going to be in Stratford, Ontario.
No kidding.
So you're welcome to visit when it's up and running.
Love to,
and that'll be installed in the fourth quarter of this year.
Oh, really? Okay.
Yeah, and that'll be a 5 kilowatt, 240 kilowatt hour system.
Wow.
So think 5 kilowatts, but for 48 hours.
Yeah.
And that's what we're designing.
And what's the location? Like, what's the application?
Yeah, so it'll actually be at a manufacturing site, a small manufacturing site.
Okay.
And it's really meant to demonstrate an application in the agricultural space.
Oh.
And so the idea is that there's many farmers in Ontario that have solar through the feed-in tariff program. But if they wanted to, one idea is that if they wanted to expand and they're, say, in an area of a wheat grid, this would be a way for them to add capacity.
Okay.
As a non-wireless alternative in a sense.
I see. Okay. So add the PV and add your technology, but not connect it to the grid necessarily.
Or even maybe a portion of their facility is off grid.
Yeah.
The idea is that many of them don't have capacity to expand. They can't add more solar. They can't add more equipment
because the grid can't take it.
The grid can't take it.
Yeah.
Similar to what we see in the CHP space, but at a smaller scale.
Sure. Well, smaller scale, except for you guys, the repeatability of all the agriculture we have in southwestern Ontario is huge, right?
Mm-hmm. Yeah. And it's also just it's a great demonstration location for us. It's close by. We can have people on site quick, and
totally.
For us, we want to learn everything we possibly can from it.
For sure, yeah.
Right. So that's the second step, and the third step of this, I'd say, early commercialization path is really to test and validate that tech in the field, and even progress on a route to certification.
Yeah.
UL, CSA.
Okay. Yes.
Right. So turning it into a product that is ready to sell commercially.
You mentioned certification. So in the last, 5-10 years, we've seen a shift in the CSA codes that govern hospitals as it relates to, and you probably remember this from INEO, that you didn't have to have diesel, you could have natural gas, but but hospitals have to have this critical backup for 48 hours or whatever it is.
72.
I knew I was gonna get wrapped on the knuckles by somebody in my office, but you beat them to it. So, do you see? And this is probably longer term, but do you see a potential for this to displace even that? From a life critical application, Scott?
Maybe there's potential.
Yes.
Definitely, especially on paper.
Yes.
And I say that because with Yumbacher, I know that with newer products, the engineering team was hesitant to install our newest products in life safety applications.
Oh, I see. Okay.
Right, and to me that kind of signals that if a huge company, right, GE Power and then INEO, Yumbacher, really takes many years to get comfortable with that type of application. As a new startup, it's not the low-hanging fruit for us.
Yeah. Right.
Longer term,
the risk far exceeds the reward, is what you're saying.
Longer term, it is a neat application. Especially in areas where you can use it for more than just backup power, as we were talking about. But it's not our initial go-to-market path.
Mm-hmm. So, James, what do you like? In your equity raise and in your pitches internally and externally, where do you see, once you get past this commercialization phase, what is the remote communities? Is that the market? Is there a secondary market where you're saying there's significant upside? Is it everybody with solar panels on their roofs and your battery, in their basement? Or is it let's get these remote communities first? The
remotes is the bread and butter here.
Yeah.
And we don't see it day to day because we live in urban environments.
Yes.
We don't feel the pain that these customers experience, and we're just not attuned to it.
Yes.
But it's a huge market, right? Like it's all of Africa, right?
Right.
Like it's
right.
like think of the Southeast Asia, like all these islands.
Yes.
There's no grid on these islands. They have to be sustained by diesel power, and they hate it. It's expensive, it's noisy, it's hard to maintain, it contaminates their soil, it contaminates their local air quality, let alone our global environment.
Yes.
And so there's a really strong impetus. And further to that, one of the other advantages of our technology is actually the temperature tolerance of it.
Oh.
So we have an ability to operate in very, very warm and cold temperatures. And companies, or technologies rather, like lithium ion, lead acid, they really suffer, particularly in warm climates.
Right.
So they have to be cooled. And that ends up being additional parasitic load. So it's upfront capital cost because you need to build a cooling system into your energy storage system. But it also is parasitic load because it's taking energy to operate that cooling system. And so when you're talking about Australia, Africa, like it's a really difficult value proposition for batteries.
Yeah.
And versus our technology will have a very, very strong value proposition there. And so the already good economics that Scott was alluding to around just replacing diesel become exponentially better.
Yeah. So let's dive a bit deeper then into the technology. So you mentioned, so it sounds like there, at the guts is this electrical chemical reaction, but I think there's some other what I would call balance of plant stuff around it. Like on the power electronic side, I heard there was an air system. It sounds like, with lithium ion, it's like, oh, there's another box and another box, and just tighten the moret on the electrical cable and away you go. But with you guys, it sounds like there's a bit more around the system. Is that right, Scott?
Yeah, and what's really neat about it right now is we've built our prototype cells in transparent material, so you can actually see what's going on inside.
Oh, that's cool.
And it's really incredible, actually. You can see, electricity being formed into zinc and dropping out, and that's just stored energy. But we do have when it's in the field, it'll be more of a sealed box. So it'll be similar to what lithium ion might look like. But so we do have some balance of plant. You can think of our technology as a really neat mix of electrochemistry and mechanics.
Right on.
We do have pumps and motors.
Okay.
The motor to drive a wiper train back and forth.
Yes.
The wiper goes maybe a minute an hour, to knock the zinc off during charging.
Yes.
Right.
So the zinc doesn't get heavy enough to fall off on its own. It doesn't like what do we call those stalactites? Like it doesn't grow and then just drop off.
In the bottom we have right now, it precipitates and it's attached very loosely to the electrodes. So we just knock it off.
Knock it off. Yeah. Okay.
And so there's a motor to drive that, and we also have a pump, again maybe a minute, an hour or less, just to circulate electrolyte, because we can get a concentration gradient in the cell.
Oh, okay.
At the bottom you're discharging zinc. Zinc is dissolving, so you can have more zinc dissolved in solution at the bottom. So we just have a pump to circulate occasionally.
Okay. Wow.
The neat thing is that the pumps and motors are pretty simple, off-the-shelf pieces of equipment. We expect, even though that they're meant to last 20 years, they're not going to, right? And so they're easy plug-and-play type systems.
Yeah.
So if you think of the service routine for our technology in the field, it'll just be about occasionally replacing pumps and motors, but they're plug-and-play. Any electrician or electrician-minded person could do it.
And on the front end, it's DC that you're generating DC.
Yeah.
Okay, so there's the power electronics that go in front of that, and have you developed that too as well in terms of the control system of how that all gets handled? That's part of your design, the IP as well.
We have a proprietary battery management system for our cells.
Okay.
But then for the power electronics outside of that, we'll use off-the-shelf DC to DC chargers and DC to AC inverters.
Yes, okay.
And those will be standard equipment, and will tie into the control systems those are currently being used.
I see. Okay, cool. Good. So you're based in Toronto?
Yeah, at Etobicoke.
Etobicoke. Oh yeah. Okay.
You got to come see it.
Yeah, I'd love to. That would be Mark. That'd be great footage to. It strikes me actually that you say it's, it's bringing me back to like grade 11 chemistry, right? It strikes me there's a huge opportunity to market this to, the decision makers of tomorrow that are sitting in grade 11 classrooms. And this is energy storage, everyone. You can see it, right? Because the lithium ion stuff is just like a black box, right?
Yeah.
But, the same way Kleenex is any box of facial tissues, you guys need to be marketing to these grade 11 kids who that's energy storage. That's energy storage.
That's energy storage.
Anyways,
Totally.
okay, so you're based in Etobicoke, but it sounds like based on the discussion, at least the long-term focus is international, right? Like your people are here, but once you start to gain some traction, there's going to be a pretty significant growth, and you're going to have challenges as far as how you scale and meet those markets internationally. Right?
Yeah, I mean, it'll be two things. I mean, we will obviously have domestic projects.
Yeah,
right. We want to start close to home, where we can be close to the technology, learn from it, etc. But we hypothesize that the biggest market opportunity is really international.
Yeah.
And it dovetails nicely with the strategy of manufacturing, because right now we have a local ecosystem of automotive manufacturers who manufacture various components and subsystems for us. And as Scott mentioned, we do assembly ourselves. But longer term, we would like to move to potentially either a contract manufacturer model where you have one group handling the entire supply chain and manufacturing assembly, as well as some of the distribution, and or a licensing model.
Right?
Okay. So you license this technology to a group that gets all of this, has access to cheap components and materials, etc., and is located strategically close to a big market opportunity, like in Southeast Asia or in India or in Africa.
Yeah.
And that can be a part of your growth strategy. So
because it sounds like different than your prior life, where I've been through that shop in Jenbach, Austria, and you have these presses and these drills, and you have a significant investment in specialized equipment. Unless I'm misunderstanding something, you have kind of standard manufacturing approaches, and it's more of an assembly of things, and that the ability to license that. Whereas is a lot it's more straightforward than trying to license somebody to build a green engine block in China, right? Is that generally correct?
Yeah, it is, and this is pointing to a very important point, which is that if you look at the wasteland of energy storage companies in the past, the vast majority of them have failed for a common reason, which is that they have proprietary technology and proprietary components that require proprietary manufacturing process.
Yeah.
So they've raised tens or hundreds of millions of dollars in capital, built up a massive factory. They have massive amounts of overhead. They're way ahead of their skis. The market hasn't caught up to the sales volumes they need, and they crash and burn.
Yeah.
The beautiful thing about our technology is that the reason it's so affordable is that it's everyday engineering. This is sheet metal stamping, injection molded plastic. This is stuff that's akin to automotive.
Yeah, right.
Which is why we can rely on Southwestern Ontario's expertise today.
Yes.
But even going forward, we can still rely on external and international capabilities as well. The cool thing, though, is that there is one component that's high tech, truly high tech, which is our air cathode. It's the part at the bottom where we inject in the air and it dissolves the zinc.
Oh, yes. Okay.
And the good thing about a potential licensing model is that we would retain that.
Yes.
And so still hold the key to the technology.
Yeah. Okay. But a piece that's probably, small enough that you can make it in one spot and ship it. Is that the thing?
Yeah. So and actually, I want to just mention something quickly about the IP. The IP is in the process.
Right.
It's not in the particular components.
Yes.
The IP is as simple as any energy storage technology where charging and discharging are combined in one cell, and gravity is the separation mechanism of an energy material. That's an important point because it's not about zinc.
Right.
We just use zinc because electrochemically it makes sense because it's cheap, abundant, has high reaction kinetics, it's energy dense, stable, reversible. We could use magnesium or aluminum if we wanted to, but we don't because zinc makes the most sense. So if anyone tries anything of this ilk, right, where they're using gravity as a separation mechanism of an energy carrier, they're infringing on our IP.
Can you say that one more time? Because that was a real nugget that we have to figure out how we pull that out. But you had some phrase and you repeated it, part of it again. Can you say that whole thing again about like what the IP really is?
So the IP is in the process.
Yes.
So it's any energy storage technology where charging and discharging are combined in one cell.
Okay.
And gravity is used as the separation mechanism of an energy carrier.
Okay. Wow.
So traditional flow batteries have two different tanks. So charging and discharging is separate.
Yes.
So we've combined that into one cell, and gravity is the separation mechanism rather than any sort of pumping mechanism.
Aha. Okay. And when you discharge, the air then is kind of blowing it back up? Is that right?
No, we inject in the air and the oxygen dissolves the zinc back into the electrolyte.
Okay.
And actually, one of the mechanical pieces Scott was talking about, the one of the pumps, it recirculates the electrolyte. It's a small pump that just
because you want to avoid those concentration gradients. Okay.
Yeah, exactly.
Yeah, I got you now.
Yeah.
So, and that IP, the protection around that IP is international, or?
We have IP granted in U.S., China, Japan, Europe.
Wow.
Yeah.
That's really slick. Wow, cool. Yeah. I get it now. It took me 3 times, but I'm glad I finally got it. So,
it's okay. It took Scott and me months.
Yeah. Well, I didn't say I could reiterate it, but that's why we record everything, so I don't have to reiterate it. So this has been delightful. Is there anything else we haven't touched on that you guys are like dying to talk about in terms of what you're working on next, or?
Maybe one thing. We're maybe a 4th stage to our development. What we're working on is lining up our next round of demonstration projects.
Okay.
And we've been quite fortunate. We say we have 3 very close to being finalized.
Okay.
And these will be demos at a larger scale, more at the 40 kilowatt, 1 megawatt hour level, so 40 kilowatts for a day.
Wow.
And those will go in the 2021 timeframe.
Okay.
Probably the latter half.
Yes.
We're looking at there's one at it's a wind facility in the U.S. that we're quite excited about.
Okay.
There's another we're actually applying. There's a grant opportunity in California right now, and it's really incredible. It's with the California Energy Commission, and they've asked for non-lithium ion energy storage technologies that have a duration of 10 hours or longer. And it's a perfect fit for our technology, and that application is actually due on Monday. So we're working on that, and we're targeting a greenhouse application.
Cool.
So you're very familiar with CHP, but this will be using excess on-site solar to charge the batteries, and the discharge will be for the irrigation load. Yeah. So it'll basically allow just the site to reduce their grid consumption, and they'll time it similarly to displace when prices are highest during peak hours. So,
the specificity of the requirements in California are driven by their recent weather events. Is that why they're saying it's got to be this long, can't be that technology? That's what the alternative is. You had somebody in the back room writing the spec for them, but it sounds like you're glad that it happened that way, but you weren't involved. It was some policy or reaction to the climate there.
Yeah, and I guess and it brings up a good point. What we're seeing in the market now. So we know that when we look at the market in terms of applications for our technology, we see them.
Yes.
There's a lot, and we come across new ones every day. But what's really neat is to see industry and regulators start asking for it.
Totally.
And so California's asking for it. It's a mix between the wildfire. They want that duration, but they're also saying, hey, we've invested a lot in energy storage. 90%'s been lithium ion.
Yes.
We need to diversify.
Oh, I see. Okay.
Because we know that to reach 100% renewable energy, their target.
Yes.
We need more than just lithium ion.
Yeah. Actually, just one point. So ARPA-E, which is part of the Department of Energy.
Yes. Okay.
So they had a day. It was called the DAYS program, Duration Addition Energy Storage. Don't ask me why the Y, which is the last letter of energy, is part of the acronym, but
it's a bit like Zinc.
And they called for technologies that can dispatch longer than 100 hours of storage.
Wow.
And why is that important? Because when they analyzed the markets and looked at California, New York, Hawaii, all these markets saying they're going to be 100% renewable, the studies concluded that at about 60% penetration of renewables, you start needing that duration of storage.
Okay.
And so, and in fact, actually, just this year, well, it's only been a month in this year, but about a month ago, PG&E issued an RFP for 96 to 120 hours of storage.
Wow.
So it's happening.
It's happening, yes,
right?
yes,
and
yes.
so that's way beyond what batteries and conventional batteries can deliver.
Totally. And I love the piece about diversity, because yesterday we had another podcast about it was Dave Tygrope, who comes from the natural gas space, and he was the champion for Enbridge to do this power to gas demonstration project in Markham, and so the spin there is hydrolysis and hydrogen, and his big thing was, listen, we want to do a lot of electrification in this province, and that's in a lot of ways that's the right thing to do, but we're going to need everything, right? We're going to need to diversify our portfolio of assets. It can't be just renewables and lithium ion. It has to be we have to leverage the infrastructure in the natural gas pipeline. And to your point, we have to leverage long duration. And so for guys like us who we just want to implement systems, we're just we're loving it, right? There's so many different technologies. Yeah. It's challenging because we've got to get our head around it all. It's not just, is it a turbine or is it a recip engine? It's not that simple anymore. But at the same time, it's really exciting.
Yeah.
So Dave, who was on yesterday, he said, well, first of all, we have to use the same units of measure, right? So gas is measured in GJs and electricity in megawatt hours, right? So let's normalize that, and then let's have a full cost, right? Not only the commodity, but also the carbon and also the cost of storage, right? Because what we don't get right now in our electricity pricing is the cost of storage, right? And so if your price point and your solution, is more competitive from a cost of storage perspective, the market should bear that out. But we don't look at it. We don't stack those costs yet, right? So, guys, thank you very much. This has been, as Mark has heard me say several times, the main goal of this is that I learn. So that's happened. But more importantly, that those who listen can learn as well, and to have fun. And this was a fun discussion.
This was very fun.
I'm excited for you guys. I think you've done a lot of great stuff already. I mean, all the money you've raised and the people you've added and the IP that you have, and we're excited to kind of watch your duck curve as you grow.
Our own duck curve.
James and Scott, thank you so much. It was
Thanks.
really fun.
Thanks,
and
Matt.
It was great to have you on Energy Radio.
Appreciate it, Matt.
Cool.
Thanks so much.
Good.